Hey everyone, this is Brian. Welcome to week 2 of CSC 143. Today would be Monday, April 12th by the time you're watching this video. Hope you had a great weekend. Before we get into today's topics, I want to go over some rhythm of business ideas for the class and talk about the single responsibility principle reading that I had you do last week. I'm so glad to see that many of you have joined Piazza and have joined in on the discussion. I'm really looking forward to using Piazza as this communal resource that we can collaborate on for asking and answering questions. I like the idea that we can share knowledge together in one place rather than having knowledge be isolated within office hours or one on one questions that I get over email. I have gotten some questions about how to get the IntelliJ uh, IDE as well as the JDK 11 install set up on people's machines. And I've heard from quite a few of you that you already have Java 15 installed. Now, it's possible to have two Java JDK installations working side by side, but it can get kind of complicated. On Windows, if you use the adopt OpenJDK installer for Java 11 JDK, it should correctly override the environment variables that make the Java C and Java commands use the adopt OpenJDK Java 11 versions. So on Windows, just running the installer should fix it, and you should get Java 11. On Mac, you may have to uninstall Java 15 before you can install Java 11 JDK. There's probably some tools out there that enable you to use both installs simultaneously, but I don't have a Mac and I'm not too familiar with using those tools. Regardless of whether or not you choose to have just Java JDK 11 or both Java JDK 15 and 11, in IntelliJ, make sure that your project configuration is set to use JDK 11. And you can do that by going to the project configuration steps that I show you in the previous project setup video. Also, speaking of projects, your Project Zero is out now. It's going to be due fairly soon, next Wednesday, this coming Wednesday, and it shouldn't take you too long. Project Zero is mostly a review of Java classes and how you can get set up by writing methods to fulfill the requirements of a program and getting familiar with the test suite and running it using the test scripts. I hope that you've already gotten started on the project and you've managed to start passing tests already so you can start earning points. Remember that the project grading in this class is very much going to be test driven, and the tests are a great resource for you to see how much progress you made so far on the project. And the more the specification that you fulfill in your implementation, the more tests that you should be passing. Project Zero asks that you implement the iterable and iterator interfaces. We're going to be seeing the iterable and iterator interfaces a lot throughout this class. As we develop new data structures, we're going to see how these two interfaces belong in these class implementations that we do, such that we're going to be able to iterate over all the elements that the structure is being stored in a linear fashion. For example, let's say we were building a linked list structure, which we'll learn about in a couple of weeks. Using the iterable interface, I can interact with that structure without knowing how the underlying structure behaves, but I'm still allowed to iterate over the individual elements of that structure. We might have a more advanced structure like a hash map that maps keys to values, and an iterator interface, an implemented iterator, is going to let me walk through the key and value pairs within that structure without knowing the underlying implementation of the hash map. You'll also see iterators and iterables a lot in other languages. Python uses a lot of iterables and iterators, and anytime you see the word generator, that's actually an iterable type that's being generated from the function itself. That's a little bit beyond the scope of this class, but it's all related, and I think it's all pretty neat. And I think you're going to be able to carry some of these skills forward into other languages that have iterable types. Finally, I want to talk about the single responsibility principle reading that I had you do last week. The single responsibility principle is the first of the 5 solid principles that I'll have you do throughout the quarter. Single responsibility principle tells us that a function, object, a class, a module should only have one reason to change. And one reason to change is kind of a complicated way of saying your class should fulfill one very specific part of your program specification. Let's suppose for a moment that you were working on a big program and it had this list of requirements. This is your specification. If you try to package everything into one class, what you end up getting is sometimes this anti-pattern they call the God class, where this one class does every single thing. It has all these interconnected dependencies within itself, and it doesn't really have any sort of sense of modular design. Modifying one function or one variable in that class causes a lot of things to also be modified because they depend on that one function or variable. Single responsibility principle encourages us to divvy up responsibilities into different isolated classes, such that we don't have to worry about how those different specifications and responsibilities get fulfilled in those other implementations when we work on a separate responsibility. The example that I give is this rectangle class that initially comes with a draw method, which is responsible for painting the pixels on a display, and the area method, which just computes the area of the rectangle. As you can imagine, these two things are not directly interrelated. The computation of the rectangle's area has zero dependency on the physical aspect of painting pixels on a display. So in a sense, that there's no reason for those two methods to be nested together within the same class. If a rectangle's area definition changes for whatever reason, then we would have to go updating the rectangle class, which updates all dependent on rectangle, which updates the entire graphical rectangle application because it needs to look at this new precompiled or recompiled version of rectangle. So what this single responsibility principle encourages us to do instead is to let's divide up this rectangle into the geometric rectangle, which is responsibility for what is a rectangle, and the graphical rectangle, which is responsible for painting the rectangle onto the screen, where the graphical rectangle depends on this geometric rectangle to give it guidance on what a rectangle is, but not for how a rectangle should be painted. Oh, here's the cat. Hello. One further advantage of this separated design is that when it comes to implementation and development, you can work on different responsibilities simultaneously or in parallel without necessarily blocking one responsibility from being developed from another. Let's say for a moment the team working on this graphics UI program has a shapes team and a drawing team, the graphics team. The shapes team can come up with all sorts of cool shapes and designs like circles or rectangles or hexagons, and the graphics team can figure out from the shapes team how to actually paint these things on the screen. Where the graphics team is more focused on the pixel by pixel display of things like colors or certain features like shadows or thickness or whatever, the shapes team can focus exclusively on what the geometric definition of certain shapes are and how we represent them. And being able to separate these responsibilities into these two different classes enables them to be developed in parallel simultaneously rather than being blocked on each other's work to be completed before responsibilities and the program can be updated. Okay, I think this intro has gone on long enough. Let's go ahead and dive into today's content about classes, references, and inheritance. References are a especially fun topic, and it's going to go over how Java is going to handle passing variables from a calling function to the body of a function itself, and what the implications are when we modify an argument, whether we replace it or we start to update the underlying values within that object. Okay, here's the show. Hello again. Welcome to another video lecture for CSC 143. In today's video, we're going to be covering classes, references, object-oriented programming, and inheritance. We're going to start out with a discussion on classes. We've already talked about classes in the last couple of lectures, and I'm sure you've encountered classes in your previous computer science courses, but I want to go over them one more time so we can have a firm grasp on the formal definition and our expectations for how they should behave. Classes are blueprints for objects, and objects are containers of state. When I say state, I mean in the state of being. You could say, I am in a hungry state. I am in a happy state. I am in a cold or hot state. We treat these objects sort of like individuals who all have their own set of properties and conditions at any point in time. A class is going to describe how each object can be, and the internal properties or fields are going to reflect the state of each independent instance. Classes are going to define methods that are functions attached to those classes that are going to manipulate that state. In one of the older examples I've given in this class, I had a class bread, and one of the methods was toast. When you called toast, the temperature of the bread went up, where the temperature, that variable, reflected the state of the bread. We can use access modifiers, like public, protected, and private, to hide implementation details. By hiding implementation details, you can abstract away certain complexities of how the class is implemented so that only the simple interface that is necessary to be exposed is provided to external clients. As an example, you may have a very complicated object, such as a data structure, maybe a linked list, which we'll learn about very soon, and the actual manipulation of the linked list for adding or retrieving variables is quite complicated, but the interface you'd like to expose to other programmers is just some simple method calls. And those public methods that are available form the interface for that class. Interfaces, formally, are like blueprints for classes. They set up the expectation of what the classes is required to implement in order for that interface to be fulfilled. Interfaces themselves don't contain implementation. Instead, classes are required to provide the implementation for all the methods defined within the interface. Classes can implement any number of interfaces together, mix and match. We've talked about the iterator and comparable interface that you're going to be seeing in Project Zero, where the iterator, or the iterable, is going to be an interface that describes things that can be iterated over, and the comparable is going to describe things that can be compared to one another. You could absolutely imagine a class that actually implements both of these interfaces. We could have a tree structure that can be iterated over by examining all the nodes inside the tree, and we could also say trees are comparable to one another, maybe by some comparison metric that we defined, like the depth of the tree, the number of nodes, and so forth. When a class implements an interface, the class must implement every method of the interface. Just like classes, interfaces are a type that can be assigned to any implementing class. Let's take a look at basicInterface.java. Up here in my basic interface file, I defined an interface, basic interface, with a string hello method declaration and an int count method declaration. Then, also in the same file, I defined a concrete class that implements basic interface. Once again, if a class implements a basic interface, or any interface, it's obligated to provide concrete method definitions for the declarations listed inside the interface itself. So down here, I have to provide a hello method, and I have to provide this count method. If I provide only some of those methods, or none of them, I get a compilation error that is going to prevent me from running this concrete class, because the concrete class is not fulfilling its obligations of the interface it's implementing. Here I've got a main method to demonstrate how you can use the interface itself as a type. On the right-hand side, I construct a new concrete class by calling the default constructor, but on the left-hand side, I declare the type of the right-hand side as a basic interface. The clever thing about using interfaces as types is you don't have to consider what is existing underneath that fulfills that interface. When you get this variable and you pass it around to other functions as arguments, or you return it, you are telling the world that this variable is a basic interface and should be treated as such. And the actual implementation is abstracted away. So here I know I can invoke the hello and the count methods because I know that all classes that implement basic interface and can be assigned to a basic interface are going to have those methods available. Unlike classes, interfaces cannot be directly constructed. There is no such thing as that interface constructor because they have to be fulfilled by a concrete class. So here, even though I tried to call a new basic interface, Java's not going to let me do it. I can't assign it to this basic interface B on the left here. One interesting curiosity is how I've defined a class and interface within the same file. This is a convenient thing you can do in Java, but I wouldn't really recommend it. It gets kind of confusing pretty quick. I do it for teaching reasons because then I can show you everything within the same file, but Java is always going to expect that you define the name of something as the same name as the file itself. So here, the file itself is called basicInterface.java, so I'm obligated to have something called basicInterface inside here. It's either got to be the class or the interface. But then after that, you can go about defining your classes on top of the same definition you've already put down. The namespacing rules get a little bit confusing. Accessing this concrete class externally is a little strange because you're essentially reading a class name that doesn't match the file name that it belongs in. So those rules can get kind of confusing pretty quickly. So in general, I don't recommend you embed two things inside the same file like I've done here, but for example purposes, I think it's fine. Let's go back to the README. The interface itself lacks a concrete implementation, so we can't directly construct those interfaces. Now I want to turn to one of the readings that I had you do last week, which was the first solid principle, the single responsibility principle. Software entities, classes, modules, functions, etc., should only have one reason to change. That's a certain way of saying that these sort of software entities, classes, modules, and functions, should fulfill a single responsibility within the program specification. We want to break up these big programs into different standalone pieces that we can implement individually, and we pass that responsibility on to these individual classes, these individual modules, and these individual functions, such that anytime we want to change the program specification in the future, the scope of that change should be implemented in practice to the responsible entities. What this rule is discouraging is building a system where everything is dependent on everything else. And it's fragile in the sense that if I want to change one little feature based on the program specification, I have to go about updating every dependent module and class. This should not be the case if we want to build scalable and maintainable software. Requirements are going to change over time, and ideally, we want to minimize the amount of change we have to actually do to meet those expectations. So what this principle is going to encourage you to do is to build out these classes with independence in mind. The classes, the modules, the functions, they should all be relegated to exactly one responsibility, or as few as possible, such that you can mix and match those little pieces of software that you're building wherever you need them. And if you need to update them, then you will really only need to affect a small piece of code. A real-world example of this sort of delegation is actually computers. We can think of laptops, phones, desktop computers as all following this sort of pattern of having different sorts of hardware to meet different responsibilities. We can talk about the computational hardware like the CPU, the central processing unit, which does most of the heavy lifting, a graphics card to do graphics capabilities, RAM, which is of course where we store our variables. But we can also talk about the physical frame, maybe the case, the power supply, and whatever cables you're plugged in. Each of those are going to have a different responsibility for keeping the computer running and fulfilling the computer's duties. We can't run the computer without a power supply. Maybe we'll use a battery or something. We may not be able to do it without cables. But the nice thing about all these things and all these parts being separated from one another and having their own independent responsibilities is that if we lose a piece, then we can go get another one. If we're starting to build computers, then we can go mix and match pieces as we'd like. If I like to make a very powerful server, maybe I'll get a really powerful CPU and a lot of RAM. If I like to buy a gaming laptop, maybe I'll go look for something with a lot of graphics. External accessories, sorry, Alexa just woke up for some reason. External accessories, like monitors, mice, keyboards, these things that you plug in and remove, we can think of these also as independent modules. Just because I have a computer monitor of one brand and a laptop of a different brand doesn't mean I can't use those two things together. And the nice thing about having these third parties build all these separate components individually is that they're going to eventually standardize on certain interfaces. I can plug in my laptop into my television because they share the HDMI interface. I can plug in my laptop into my desktop monitor because they share the DisplayPort interface or the VGA interface. Mice and keyboard, they tend to share the USB interface. We can have these independent, standalone modules of complexity that expose these relatively simple interfaces that are going to let us mix and match our requirements as needed. Okay, now let's talk about references and reference types. I understood that reference says your computer every day. We know about primitive types already. These are easy and familiar, pretty space efficient. Char takes up 1 byte, int takes up 4 bytes, float 4, double 8, long and 8. Classes, we've talked about, are a simple kind of data structure, a means of organizing this data together. A class can store any number of variables, including arrays of variables. A class can store a mix of types. A class stores all these variables contiguously next to each other. And methods are actually stored next to variables as well. These methods are essentially blocks of code that are next to the class definition, so that when you call those methods, that they're very easily accessible, so long as you have a location for that class. let's take a look at scratch.mixture in mixture.java. And really all I want to demonstrate to you here is how you can mix and match all sorts of types inside classes without limits. You have to find a class mixture. It's got a public char C, a protected int I, and a private double D. Scroll down a little bit and I have something a bit more complicated. I've got a mixture of many types, a char C, int I, double D, an array of integers. This is the array syntax in Java, an array list of object types, and some other interesting things like the basic interface. We talked about that just a little bit while ago. This is essentially a reference to something that's abstract. I don't actually know what implements the basic interface, but I do know that whatever reference this stores is going to point to something that does. Finally, check out this interesting definition. Mixture is a mixture of many types. So this is actually a recursive definition. Mixture of many types contains a mixture of many types. How is that physically possible? If mixture of many types contains itself, then it's going to contain itself and itself and itself and itself, all the way up to infinity. There's no physical way we can store this, right? Well, thanks to the power of references, we're going to be able to reference a variable from ourselves that is also of the type of ourselves. And what's really happening under the hood here, that we're going to talk about very soon, is how for all these object types, we're not actually literally storing those bytes back to back. Instead, we're storing a reference to another location that includes those bytes that make up the underlying object. And to demonstrate that, let's take a look at the whiteboard. Let's start off with these primitive types on the left. Char is 1 byte, int is 4 bytes, double is 8 bytes, and we can just imagine these as taking up blocks of memory contiguously. Then we go about defining a class like mixture, and primitive types, well, these are still stored byte-wise, so we'll get essentially a mixture class that's going to embody the char, the int, and the double, and these bytes are more or less stored back to back. Now let's zoom out a little bit and talk about the memory layout. Imagine this big bar is kind of like your big stick of RAM. In memory, you have addresses that represent the location of each particular byte, kind of like street addresses in real life. If I have an integer, a char, and a double, these have to live in memory at some point, because we, of course, have to use those variables later. So when I declare an int, it might take up a spot at address 100. When I declare a char, it might take up a spot at address 104, and so forth for all these other types. And when I declare one of these object types that take up more space, it's going to, of course, occupy more space. Memory addresses are nothing really special. They're just integers. They behave much like street addresses. If I give you a big, really long street, and everyone on the planet has to live on that one street, well, everyone's going to live somewhere, and you can address everybody by just some number offset based on how far they are from the very beginning of the street. If the smallest address is 0, then every address is just going to be the number of bytes that are offset from that 0 location. Here, my first variable starts at byte 100, but then because that variable itself takes up 4 bytes on its own, the integer, the next variable has to be set at 104. This char internally only takes up 1 byte, but you might be surprised to hear that practically, in terms of system design, we tend to store variables at certain offsets, in this case multiples of 4, for a 32-bit machine typically, because it helps with the actual act of looking up different variables. That's a little minor detail that I don't expect you to know, but it's kind of a fun fact, and you're going to learn more about it if you ever take a systems course. In any case, what I'd like to convince you here is that we do need to store everything in memory, which is pretty obvious, and everything in memory is going to get an address that represents its byte location where the underlying bytes are stored. Now let's talk about what happens when we try to store a class that contains object types. We know that the primitive types are just plain bytes, that's not too complicated, but what happens when we store classes that are themselves containing other things? This mixture of many types has an int a mixture m, and an array list list. And if we try to store all these things compactly inside a single class, it's not going to fit. If the array list is a potentially infinite size array, we physically can't just allocate a fixed length of memory and then put the entire array list in there, because we're eventually going to run out of space in that array list. So instead what we do is we're going to store a reference or an address to the actual underlying location of the object types we're referencing here. So the mixture of any types is still going to have that int a. The primitive types are just stored bytewise. So that's going to occupy 4 bytes here. But then the mixture reference and the list reference that we're showing are actually just going to be street addresses that locate the actual location of those underlying classes. In the case of that mixture class, where it just has some primitive types, I'm going to reference variable m by its location. Maybe it's at 116. Well, if I have a 32-bit computer, then I can reference all my addresses within 4 bytes. So I'll just have an integer in the space where m belongs that is going to be equal to the true location in memory of where mixture lives. Same thing happens for this array list here. Let's say this array list was located at byte 132. My list variable inside mixture of many types is going to be 4 bytes, an integer reference, that is going to be set to the true location in memory of where that array list belongs. Array list itself, which is going to be referencing many other objects on its own, is going to do the same thing inside. Each index inside the array list, each value inside the array list is going to be yet another reference, another integer that points to and locates an object underneath that the array list is going to point to. So that way we can go from the mixture of many types to the underlying array list to the underlying values within the array list without having to worry about how we store everything within the same box. So the big takeaway is that primitive types are going to be stored directly as values, but classes are going to be stored as a reference to their true memory locations, where those true memory addresses are just plain integers. They're nothing really special beyond what we have with those primitive integers that we saw appear in the mixture. One of the problems that those references is going to address is that at scale, class is going to lose practicality. If I have an array list inside my class and I try to store it by value, I physically try to fit the array list inside the class, I'm going to run out of room inside that class. I don't know what the fixed size of that class is going to be because it's going to keep growing and growing and growing. Java itself we call pass by value, meaning that function arguments are copied as bytes. Well, what do I mean by that? Well, let's suppose we call a function like hello or greeting, I suppose, in project 0. When I pass in that string argument into that function, Java being passed by value means that entire string is going to be copied over. But that method doesn't scale up, right? If I have a very long string and I'm copying things in and out from different function calls all the time, it's going to get slow over time because I'm going to have to do so much copying. The longer the string, the longer the copy operation takes, and then the longer the method call takes. So pass by value, which is going to copy stuff, isn't going to scale up for us if we do everything in a primitive way and we go about copying all those bytes every time. Arguments are going to get too big. It's going to take up too much stack space for all those variables to exist. And the return time is going to be too big as well. If I try to return a large string, then I have to copy that whole string all the way back, pass by value. It's not going to scale well for us. So let's zoom out a little bit, go a little bit back in time and talk about pointers. We kind of addressed what pointers were when we went at that whiteboard and we told you about all those different locations in memory that things are addressed at. And practically every variable is going to have a memory address. That's going to point to its location stored in physical memory. We've already gone over that. That's just going to be a plain integer that's really no different from the primitive int. So rather than copying entire objects via pass by value, what if we went about copying the pointer to the object, copying that pointer to their object locations? Copying an int is relatively easy, and knowing the location of variables is also relatively easy to define. And we can still get the benefits of pass by value, that is getting copying out of all of our variables, and when we call functions as arguments and we return variables from arguments, copying that integer, that pointer to a location is going to be much cheaper than copying an entire structure, an entire string, or an entire array list. Quick side note, the difference between a 64-bit and a 32-bit machine is the size of the pointer data type, 8 bytes and 4 bytes respectively. So on a 64-bit computer, which is the vast majority of computers these days, addresses are actually going to be long in width. Let's drive this point home about pointers by looking at a C file in the C programming language. Here's some C code. I don't expect you to necessarily have a C background, but I'd say it's not too hard to digest. We have a struct A definition. A struct is a lot like a class, it just doesn't have methods attached. C is not an object-oriented language, so we can really treat structs as just buckets of variables. I have a struct A, it has an int I and a char C. Then I have three slightly different methods here. All right, these aren't even methods, they're just standalone functions. The first one is print A by value. The argument type is going to be a struct A, so that struct we just defined, and all it's going to do is print to the console the I and the C fields. The next two functions are a bit more interesting. The first one is called modify A by value, which is going to take a struct A, and it's going to assign the I property to 333 and the C property to the V character. This function, modify A by pointer, is going to accept a struct A pointer. In C, the star indicates that the type is going to be a pointer type. So up here, I accepted a literal struct A. Down here, I'm accepting a pointer to a struct A. Inside, I'm going to be modifying the I to 999 and the C to this P character. And the reason I have to use the arrow syntax is I have to tell the program that A itself is a pointer type, and I have to dereference to the thing that lives at the end of that pointer and assign the fields inside that thing. So a very subtle difference here. This one takes struct A's byte-wise, so it's going to be a full copy, and this one's going to take an integer that represents the location of a struct A that already exists, but otherwise is not going to be copied in. Now let's turn to my main method. I define my struct, which is a struct A type, and set its I field to 111 and its C field to the character A. Then on line 27 here, I'm going to use the ampersand operator to retrieve the memory address of my struct. On the left-hand side here, I see the star, which indicates that the type is going to be a pointer type. This is a pointer to a struct A, and I call that my pointer. So struct A, my struct, is going to be a contiguous set of bytes that includes an integer and a character, whereas my pointer is really just a plain integer that just so happens to point to struct A's. The first thing I do is print out my struct A by value. And remember that print A by value takes a struct A as an argument. Because it takes a literal struct A, what actually happens in C is that it's going to copy all the bytes that compose my struct and pass them in to the print A by value function. C is passed by value, just like Java is passed by value. It's always going to copy the arguments in and the return values on the way out. Then, when I go about modifying A by pointer, we're going to copy the struct address on the way in because I'm passing in my pointer here. So I call modify A by pointer, which takes a struct A pointer, and once again, C is passed by value, just like Java is passed by value. So the 4 bytes that are composed of my pointer that locate my struct are going to be copied in as 4 bytes to this lowercase a here. Then I reassign those variables inside the struct A to be 999 and P. Finally, in the third step, I'm going to do a modify by value. I'm going to copy my struct, all the bytes that compose my struct, into the modify by A value function and see what happens. Remember that modify A by value takes a plain struct A, which means the entire struct gets copied into the argument and then modified. Let's try actually running this program. You don't have to do this on your own machine, so just follow along in the video. Let's see, where's this file located? Pointer.c inside of Scratch. And I'm going to compile this file using GCC, which stands for the GNU C compiler. I'll pass in the argument -o and the name of the executable I'm going to generate. Then I'll run the executable using /. Okay, let's see what we got. In the first step, we got the actual value of a, which was just 111 and the letter a, which of course is what we defined up here, so it's what we expected. The next thing that happens, we called modify a by pointer, which set the internal values to 999 and p. And we see that that's actually reflected when we print out the value of a. But here in this third call to modify, modification by value, when I passed in a copy of my struct, even though that function changed out the variables to 3, 3, 3, and v, we don't see that get reflected inside the printout statement. So what happened? Well, modify a by value takes a struct by value. And when it takes a struct by value, I'm actually copying all the bytes of my struct into the argument of modify a by value. So inside here, this lowercase a becomes a copy of the outside a, and then modifying that copy, of course, is not going to change the outside a. So once again, modify a by value accepts a struct by value. The argument type is a plain struct, which means I'm going to be passing in a copy of all the bytes that I'm calling the function with. Therefore, this lowercase a here is a byte by byte copy of the struct I had initially defined in my main method, and changing that copy doesn't at all affect the struct inside my main method because it's a copy. This is in contrast to what happened when I modified a by pointer. Because I'm passing in my pointer here to this modify a by pointer function, yes, indeed, it's still passed by value, so I'm copying the pointer from my main method to this lowercase a here, but the two pointers are going to point to the same thing. My pointer on line 27 locates my struct. The copy of that pointer is also going to point to my struct. So when I modify the fields inside that struct by dereferencing that pointer, it's going to go modify the underlying struct that is constructed inside the main method. So big things to keep in mind here. There's one way we can do it where we modify the underlying values, and there's another way we can do it by modifying the copy. Now, that was maybe a lot of code that you haven't seen before, or some code that you're not familiar with, since you might not have a C background. And in practice, it's actually quite a pain in the ass to use pointers. You can make pointer arithmetic mistakes. In C, pointer types are really just integer types, which means we can add to them and subtract to them, just as we would with plain integers. And if you add numbers to pointers, it's kind of like adding a number to a street address. It doesn't always make a lot of sense, and it can take you to the wrong location. There's no runtime type validation either, which means if we make a pointer arithmetic mistake, such as identifying an array offset that is beyond the length of the array, we can actually read in a space of memory that's invalid and not the actual type we're expecting. There can be memory leaks caused by pointers. If I generate a pointer that allocates some space in memory by calling malloc, and then I fail to free that location of memory, maybe because I dropped the ball and left that pointer behind somewhere in a function call. Then we have to be conscious of this pass by value versus pass by pointer by value experience. I showed you how in these two very similar function definitions, one of them modified the outside world and the other one did not. However, they were still both pass by value. It just so happened that one of them, the one that actually performed the modification, was passing a pointer that got copied that was pointing to the same underlying object. I think you'll be thrilled to hear that Java is not going to expose pointers to us. Instead, it's going to expose something called a reference, which behaves kind of like a smart version of a pointer. The difficulty of using pointers caused the Java engineers to come up with a different kind of way of referencing items that are stored in memory from a distance without having to deal with the technical hassles. A reference in Java is like a pointer. Internally, it is a number which locates an object in memory. That number is an address. However, it comes with some key differences when compared to pointers. The first is that the underlying value the literal memory address number, is not provided to you. Therefore, you can't perform arithmetic on this value as it's abstracted away to us. In C, we could actually treat that struct A pointer as a plain int, meaning we could add to it, we could subtract from it, we could modify it just like an integer. In Java though, references are not going to let us do that. And they're not going to let us do that by nature of not letting us see the actual number at all. The second difference is that the reference is going to have a fixed type, and it's not going to allow you to reassign it to an incompatible type. In the C example, we had a struct A pointer, and by nature of it being just a plain integer, we could relocate that pointer to something else by reassigning it to a different address. However, C is not going to stop us from assigning it to an address of an object that's a different type. In Java, Java is not going to let us assign references to types that are not compatible. For example, I'm not allowed to assign a class that does not fulfill the basic interface because those two things are incompatible. In Java, as it turns out, every object, every non-primitive variable, is actually a reference. It's almost as if we had said basic interface star in front of the basic interface variable definition, except every object is inherently a reference, so Java's not going to have the explicit star operator like we see in C. Instead, we're just going to treat every object variable as if it were a reference already. So every time you use the new keyword to construct an object, the instance gets constructed in memory, and the variable on the left-hand side is going to store a reference to that instance. Once again, Java is still passed by value, but all function arguments are passed by value as references. References, by nature, just being integers on the inside, means we can copy references around and return references with ease. Reference arithmetic does not exist, as described, and Java actually has something called a garbage collector that's going to do reference counting to keep track of how many references still exist to an object, and then clean up objects that are unused. Let's take a look at how that behaves in practice in reference-test.java. We'll start at the top with a class A that takes an int I. It has a one argument constructor that accepts an integer I and simply assigns the I field to that value. Next up, let's define some local A instances. I've got an A of 0 here and an A of 1 here. On my comparison for line 27, I'm using the double equal operator to compare the underlying addresses of foo and bar. Remember how in the first lecture we used dot equals to compare big integers together? Well, the reason we didn't use double equals is because the double equals primitive equality when comparing object types is that it's actually going to compare the underlying memory addresses. So foo and bar being two independent instances of A, meaning they live in two different spaces in memory, means that foo double equals bar is always going to fail. Now let's see what happens if I assign foo to b bar. Reference foo is now going to point to the instance that bar points to, and foo's original instance gets garbage collected. Remember, in Java, every variable that's an object type is actually a reference, so this is kind of like an A star here. Foo is really just an address to an A, bar is also an address to an A, and when I update foo with bar, I'm replacing foo's original address with bar's address. That is going to let me perform this assert true here. I can use the primitive double equals to validate that foo's underlying memory address is going to be the same as bar's underlying memory address. Remember, I still don't actually know what the literal values are here. I can't actually determine exactly what integer foo or exactly what integer bar exist at, but I can ask Java to compare those two things. Let's go ahead and run this test just to validate ourselves. Whoops, looks like I forgot to comment this out properly. Okay, great. Then down here, I just validate that foo's I and bar's I are going to be the same now that they point to the same thing. Now let's take a look at this function on line 41, assign a argument. This function takes a single argument, which is a type A, and we call it argument A. Remember that in Java, everything is passed by value. But it also happens so that in Java, every variable can be treated as a reference. So that when we copy into assign A argument, when we pass a value into assign A argument, I'm really passing a copy of the location of argument A. Now take a look at what's happening here on line 42. I'm trying to perform an assignment on argument A, and I'm trying to assign it to A of 5. But what I'm actually telling you is that this A actually gets garbage collected the moment the function exits. Why is that the case? Well, let's see what happens in this test. Let's define an A foo, and then define a bar that is a reference to foo. Well, more strictly speaking, bar is a reference to an A that is equal to the reference foo, so they both point to the same underlying A instance defined on line 48. Then I call assign A argument foo. Remember that in Java, everything is passed by value, so I'm copying foo into the function arguments, but also in Java, everything's a reference. So I'm really just copying an integer that represents the location of this A that I constructed. So there's an integer that is in foo, an integer that's in bar that's equal to foo, and I pass in a copy of foo's integer into assign A argument as the argument. So there's a number inside argument A that's equal to the number that is inside foo. But when I assign argument A to a new A of 5, what you actually don't see happen is that the outside A gets updated. And the reason for that is argument A is a number, and I'm replacing that number with a new value. That is the memory address returned by new A of 5. But by nature of argument A being a number that is a copy of the number that was in foo, overwriting that copy has no effect on foo. Let me repeat that. Foo is a reference to an A. Foo stores a number that locates an A object. When I call a function and I pass in an argument, Java is passed by value, I'm copying that number and placing it inside the argument here. Because argument A is just a copy of a number, overwriting that number has no effect on foo. Remember, foo got copied into argument A, so reassigning argument A has no effect. Whatever new A of 5 returns, it's just going to get stored in argument A, updating the number of argument A, but not updating the number of foo. So I say this gets garbage collected because the moment this is constructed and the function exits, nothing actually references this new A of 5 externally, and it's no longer useful to us. We leave the scope of the function and it's impossible to access argument A. One interesting effect of this, IntelliJ actually tells us parameter can be converted to a local variable, and it's telling us this because we don't actually do anything with this argument that is meaningful beyond just declaring a local variable. Remember that argument A became a copy of foo, and then we immediately overwrote it. So we did nothing useful with the original value that foo gave us. Down here, I validate that my foo is unchanged. The value still points to new A of 0 because bar was a copy of foo, and then even though I called assign A argument, foo did not change and bar did not change either. Now let's take a look at this example. Modify A argument. Java is still passed by value. It's always passed by value. But the key difference here is I'm using dot notation to look up the field inside argument A and assign that to 5. In this example, assign modify A, I take an argument A, passed by value, I assign it to a new A, and then I modify the field of that new A to be 5. And then here in A modify return, I take an A, change out the A's I to be 999, assign that argument to be a new A, and then return that A. Remember, Java is passed by value, which means all these get copied in, and return values get copied out. Now let's see what happens. In my modify test, I generate a new A with a 0, and I make a bar that's just a backup copy of foo. Then I call modify A argument of foo. What happens? Well, I pass in a copy of the reference foo. So if foo has an underlying value, some address to an a, I copy that underlying value inside modify a argument. So that number that gets internally stored in argument a, which is a copy of the number internally stored in foo, locates the a that we had originally defined out here on line 77. Then, on line 61, when I use the dot notation to look up the field I within argument A, well, this is like that arrow operator we saw in C. I'm actually doing a dereference of the I field within argument A. And because argument A's underlying value points to the same location as foo's underlying value, this is actually going to perform a modification to foo and the underlying A that's located there, because I performed that dereference and looked up the field for the location of the argument that I passed in. We can see this effect in these assertions. Even though A starts out as 0, modify A argument does indeed have an effect on foo's underlying I value, and that value has now changed to 5. It is no longer the case that it stays at 0 like we saw in the previous example. We still do see here though that foo itself, the underlying address, is unchanged. The number location of where the A is has not changed, as bar, the backup, is remained unchanged as well. However, unlike in the previous example, where there was no change because we tried to overwrite a copy, down here, there was a change because even though we had a copy of the number, we looked up what was at the end of that number and reassigned the field on the inside. Now, I don't have test cases for these other functions, but what I would encourage you to do is download these class notes and play around with these function calls and see what happens to them. Your intuition should generally tell you that this assign modify a function doesn't affect the outside world because line 65 overwrites the value within argument a, and then modifying that new value doesn't change out the a that I passed in. Modify a return is a bit more interesting. I modify the value that I passed in, and then I replace it with a new a. Your intuition should generally tell you that this modification does affect the outside world, but then this modification, well, this update, the reassignment of the copy, doesn't affect the outside world. Because remember, argument A is a copy of whatever I pass into it, and when it points to the same underlying value as what I passed in, then it changes the underlying value, but replacing that copy has no effect on the variable in the outside. Now, if I return it though, well, that's going to actually return a copy as well. So this returns a type A, it's a copy of type A, and whether or not I assign it to a variable in the outside world decides whether or not it affects the outside world. If I don't assign or save the value returned by modify a return, then this A essentially gets discarded and garbage collected. So, general observations. Because arguments are passed by value, the reference gets copied. Functions cannot change the original address of the reference, but they can change the instance that is being pointed to by the reference. In both of these examples, foo and bar remain the same and unchanged by the end of the test. However, based on how we treated that pointer inside the argument, we may or may not have updated the underlying value inside. Just for formality, let's talk about this. The double equals operator is going to compare two objects by their underlying memory address. I like to call this physical equality because it validates that two objects being compared are physically the same object underneath. Dot equals is a method that we will explore very soon, which should compare two objects' underlying state. We need to differentiate between these two equals operators for a very important reason. One of them is strict equality. It is to say this is that other object. These objects are one and the same. They live in the exact same spot in memory. This dot equals is the value-wise comparison. What this is going to ask is whether or not two objects are semantically equal, not just physically equal. One easy example is two different strings. Let's suppose that when you register for a user account on some website somewhere, you type in your name and you make your account. Then later, you want to log in and you type in your name again. Your name is going to be a different string in those two circumstances that you logged into the web page. You passed the string the first time to register your name, and you passed in a new string to log in. We can't use double equals in those circumstances because we have two separate strings. But we should use dot equals, which is going to do the value-wise comparison. It's going to compare the two strings byte by byte, and it's going to validate that you have the username that you matched what you registered with. So, in summary, double equals, physical equality, has to be the same object underneath. Dot equals is going to do a state-wise equality. It's going to compare all the values within the object and expect those to match up, not necessarily the physical equality and the same physical location in memory. We're going to have two independent objects that have the same state underneath and call those two things equal. Let's take a look at the whiteboard just so we can drive this point home. We said that Java is passed by value, arguments and return types are copied, and for reference types, the reference is what gets copied because every object type, every object definition as a variable is really just a reference to that object. So let's suppose I had an A class, an A instance with a value I of 3 that lives at address 500. In this void assign, I take an argument A, which is of course a reference to an A, and I reassign its value to be new A of 2. Well, when I call new A of 2, I'm building a brand new A and I'm looking at a new address. Let's say it's 512. However, because this 500 here is actually just a copy of the A address on the outside, what I've actually done with this equals operator is essentially overwrite that 500 with 512. And you can imagine how if I have 500 saved elsewhere in the outside world, it doesn't affect that outside world A. Has no effect on the outer A, argument is a copy that gets reassigned. Now let's take a look at this right-hand function, modify A, where instead of reassigning using the equals operator, I first do a dereference using the dot and look up a field within that A. Well, what happens here? This is going to modify the argument even though it's a copy, because this A over here is going to reference the outer A instance. So remember, this A over here, located at 500, I copy it into this argument as 500. Then when I perform a.i, I look up the underlying value at address 500 and update the I field. So this function indeed is going to change up whatever value is inside this A that I initially declared in the outside world. And the big difference is, in this assigning example, I've replaced the value inside the argument, which is actually a copy, so it doesn't affect the outside world. But here I perform an actual dereference, very much like that arrow operator we saw in C, and modify the underlying field at that particular location. That's all I've got for references. I really encourage you to go about downloading these class notes and playing around with the assignment and lookup so that you can bolster your confidence in understanding how references behave in Java. I think the key point to keep in mind is that Java is passed by value and everything's a reference, but it can be kind of hard to recognize where references get updated and where values get reassigned. So again, very much encourage you to download these notes and play around on your own time. Now let's turn to a different topic, which is inheritance. Object-oriented programming has three main pillars. Inheritance, which we'll talk about today, this notion that classes can be extensions of other classes. Polymorphism, the idea that classes that fulfill the same interface can be used interchangeably where that interface is expected. And encapsulation, the notion that classes expose simple interfaces that are hiding complex implementation underneath. We've already explored a little bit of polymorphism and a little bit of encapsulation. Polymorphism we actually saw when we discovered how to use interfaces. When we learned how Java interfaces can be fulfilled by a particular class, we learned how those interfaces obligated those classes to fulfill certain methods. And then later, I could assign concrete classes to those interfaces or those variables or the interface type. Furthermore, I could replace those variables with other concrete classes that live in a different hierarchy, so long as those classes also implement the same interface. The example we had gone over was the shape2D object, the shape2D interface, which was fulfilled by the circle and the rectangle, and I could place the circle in the shape2D as well as the rectangle in the shape2D because they both fulfill the same interface. Encapsulation is very much like abstraction. It's this notion that we can hide complicated implementation details with a relatively simple interface. Encapsulation is a bit more specific. It tends to refer to the literal access capabilities that are exposed by a particular class. We've seen these with the keywords public, protected, and private. We'll learn more about that pretty soon. But encapsulation and abstraction very much go hand in hand, and it's this idea that we like to keep complicated details like internal variables and state contained so that the outside world doesn't have to interact and know about those details. Today we're going to be going over inheritance in depth. Inheritance is a form of code reuse that allows classes with similar behaviors to share a common base. When a child class extends a parent class, the following things happen. The first is that all properties are inherited. Those that are public or protected can be accessed from the this keyword. All methods are inherited as well. Those that are protected or public can be accessed via this. Remember, the private keyword indicates that a class owns those properties or methods and is the only class definition that can access those properties or methods, which is why even child classes down here aren't going to get access to them. Constructors do not get inherited. This may seem as a surprise to some of you, but this is actually very much the case in Java. And the reason is because we'd like to have a very specific set of circumstances for constructing an object that is specific to a particular class type. As we extend classes, we're going to come up with additional fields and other properties we attach to that class. Therefore, it may not be simple enough, or it may not be sufficient for us to call a parent constructor because that parent constructor is not aware of what fields need to be initialized in the child classes. Similarly, if a child class does not provide any constructors, it doesn't really make sense to call a parent constructor because there's essentially a piece missing, right? The child class never gets constructed if you never call that child class constructor. So this is very much by design. Java is not going to have those constructors be inherited, even if the parent declares them public or protected. There is one small exception to this rule, which is if you don't define a constructor at all. Parent classes that don't define constructors have something called a default constructor, which is a constructor that takes no arguments and initializes whatever variables on the inside to be some reasonable default value. If you have a child class that also does not define a constructor and inherits from this parent class, well, the child class is going to have that default constructor as well. So in a way, the child class gets the parent class's constructor, but it's not really an inheritance. It's more like a default definition, which happens to do nothing particularly interesting. The child class's constructor will also set reasonable defaults to whatever fields are defined in the child class. Primitive types tend to be set to something uninteresting like 0 or false, and object types tend to be set to null. Because of this, the child class is obligated to actually call the parent's constructor using the super keyword. That way, inside the child, you can initialize whatever variables in state need to be initialized, and then you can go off and defer the remainder of the construction process to the parent via using the super keyword. The super keyword is kind of like the this keyword. Remember that this is essentially a keyword that refers to the current instance. Super still refers to the current instance, but it's specifically referring to the parent portion of the instance. So you can use super and the dot operator to access methods from the parent side. The result of all these effects is that the child is going to expose the same interface, that is, the public methods, as the parent class, because those public methods are going to be inherited by the child. Furthermore, the child may optionally modify the parent's original methods, choosing to override them, but it is not obligated to do so. The child can optionally have methods that the parent does not. It can define its own methods if it would like to. So, let me rephrase that. The child can optionally modify the parent's original methods. It's not obligated to do so. If it does modify them, the child methods are going to get called, and we'll talk about that soon. If it does not modify them, the parent's methods are going to be called, and the child is also not bound to only use the parent's methods. The child class can optionally define methods that it would like to define for itself. Let's take a look at a relatively simple class hierarchy with place, school, and university. Let's start out with this place class. It's got a protected string name, a single constructor place that takes a string name, which assigns that value. Then it's got a get name that returns that string, and a toString which simply returns whatever get name returns. Place itself is a top level class. It doesn't inherit from anything, but there is a hidden parent that all classes inherit from, which is of course the object base class. So down here, I have a toString method that is actually an override of toString, because the parent object, the global object that all classes inherit from by nature, is going to have its own toString implementation. We've talked about briefly how toString is essentially how Java converts object instances into strings, and the default implementation provided by object isn't particularly interesting. If I don't have this toString definition, it's going to give me some gibberish. In fact, fun fact, the default Java implementation of toString prints out more or less a hex representation of the live address that object lives at memory. And you can explore that on your own time if you choose to remove this toString call and then try to call toString on this class. But that's not super useful to us. It doesn't provide us a meaningful string description of the actual object. So we choose to override toString such that anytime a client, a place, calls toString on an instance, it runs the child's implementation and returns this.getName. Now let's see what happens when we extend this class with school.java. Here I've declared public class school extends place. And the extends keyword is where the magic happens. It tells Java that school is going to be a place type, and school needs to inherit all the public and protected methods and fields of the place. Remember that place had a protected string that was the name, and school is going to tack on another field, which is this protected hash set of string students. You may not have ever used the hash set before, and that's totally okay. We're going to treat it as an abstract type for now, in that we're not going to worry about the underlying implementation details. We're just going to use the public methods provided by it and treat it as a class that is going to behave like a set of items. Very much like how the array list is essentially a list that grows in size that stores a generic type, the hash set is a set of things. Formally, a set is a bag of items that has no duplicates. As you can imagine, I can add students to this set, and I can't add a duplicate student to the set. It just won't grow the set any further. Set's interface is going to be relatively simple. I can build a set using the new keyword and calling the constructor just as I would an array list. Check out this super call here on line 9. Remember that in a child class, I'm obligated to call a parent class constructor because the parent class still needs to be initialized. So here, I can take in the name field provided in the school argument and pass it up to the parent class to be initialized as the name field in the internal string. Then after that, I can go about initializing whatever variables are defined in the current subclass. On lines 13 and 17, I've gone ahead and defined some new functions that are new to the school but not present in place. I've got enroll, which adds a student to the roster, and expel, which removes a student from the roster. Once again, even though we don't know how the hash set necessarily behaves under the hood, we do know the basic interface that it provides us. In this case, I'm showing you add, contains, and removes, which all behave as you might expect. Add's going to add the string into the set, contains asks and returns a boolean whether or not the student exists inside the set students, and remove is going to remove it from the set if it exists. You can of course read more about this on the Java documentation, but what I really want to emphasize here is that we don't have to know how the hash set works, we don't have to know how it behaves internally. We can still use the class based on the public methods it gives us, which is a nice layer of abstraction so we don't have to think about it. Down here, I've done yet another override of toString. In this particular case, the school is a bit more complex than place. It has more meaning in that there's more internal state going on, so the conversion of school to string should be something meaningful as well. Remember that the place definition of toString simply returned the name. Here, the school definition of toString is going to return the list of students combined in a comma-separated value. I'm also going to use the super keyword to call the parents toString method so I can get the name of the school back. The reason this is possible, this call to string.join, is because hashset itself actually implements iterable, that interface again that declares an object can be iterated over. String.join allows any iterable object to be passed in as the second argument, and it's going to join the string representation of all those elements inside that second argument using the first argument string, which is this delimiter here, which is going to be this comma. So what I should expect to see out of this function is the name of the school, colon, and a list of students separated by comma. Let's take a look at place test and see how it all behaves. In my first test on line 13, I declare a place NSC, I give it an argument North Seattle College, and I expect that the toString call is going to return North Seattle College. Here, the toString is of course overriding the base toString implementation of the object, so I actually get my implementation, which prints out the name, or not prints out, but returns the name that I expect. Next, let's take a look at the school test. Here I've made a school type NSC, that is North Seattle College, and thankfully, it being a school, I'm exposed certain methods that the place did not have, like enroll and expel, which were unique to the school. NSC.enrollJohn adds John to the school. Then I assert that North Seattle College contains John when I call the toString method. Once again, toString itself being an override causes the call to toString to refer to this specific school implementation, not the parent's place implementation, which of course only returned the name, and not the base object implementation of toString. Then down here on line 25, I expel the student John, and then I get North Seattle College with nobody inside. So this all should behave as you might expect, and perhaps the only particular thing that I want to emphasize is the behavior of these overridden methods. Somehow Java is going to be smart enough to figure out which implementation of toString to call. And it's actually quite simple. It's always going to refer to the most specific subclass implementation that's available. So by nature of this school being, well, a school type, even if I choose to refer it in a variable of a different type, perhaps one of the interfaces that it chooses to implement, the toString method call is always going to go narrow down and find the actual concrete implementation provided by the most specific type and call that. That's why we get the toString output of school and not the toString output of place. Let me emphasize that in a different way. I told you how, by nature of school extending place, that all schools are places. So I can actually write on the left-hand side the place type and fulfill it using the school type. Very much like how I could declare an interface on the left-hand side and fulfill it with a concrete class that implements that interface on the right-hand side. Now I do get some errors here. NSC.enroll is not a method because place does not have the enroll method. Same thing goes for expel, so I can't quite show you in this exact example. But what I can do instead is actually assign it to a different type of variable. Let's go ahead and make a place, NSC2, and assign it to NSC. This is possible because, well, NSC is a school, and schools inherit from place. Therefore, schools actually fulfill the same public interface that place does, and I can assign a school wherever a place belongs. Granted, I lose access to these more specific methods that are provided by the school, like enroll and expel, but those methods are actually going to be sort of hidden inside this concrete implementation. Now what happens if I call nsc.toString? Well, place itself had a toString implementation. School had a toString implementation. Which one is it going to call? Well, just as I said before, Java is going to go figure out what is the most specific concrete implementation available for the function. regardless of how I necessarily refer to the object that's being invoked on. So despite the fact that I'm referring to NSC2 as a place reference, Java recognizes that the underlying type, the most specific type available, is the school, and it's going to go call upon the school's toString method. Let's make that explicit with this assertion here, and then run this test to verify. Great. So even though place has a toString implementation, school has a toString implementation, explicitly referring to this variable as being a place type is not going to stop Java from going to go find the most specific concrete implementation available, which happens to be school's toString method. This is very much polymorphism at work. This notion that child classes can fulfill the place of parent classes, and yet those child class methods are the ones that get called. The process is entirely transparent. I can't see directly that this toString call is actually the school's toString call from here, but Java's going to be smart about it, and it's going to go find that most specific implementation it can find. We're going to see much more polymorphism in the coming weeks. Let me show you one more class in this hierarchy of ours, which is university. Here, university is going to extend school. Here's another hash set. We'll make it the bucket of undecided students, students who haven't decided what major they'd like to be in. And then we'll make a hash map of departments. Once again, you might not know what a hash map is. You might not know how it's implemented underneath. That's okay. Let's just learn about it real quick. A hash map is a dictionary mapping that takes us from string to set. A dictionary is essentially a structure that stores keys and values, where keys are like words in a dictionary, and values are like those respective definitions. It's going to associate the word with its given definition. Here, the hash map is defined in such a way that I'm associating a string type on the left as a key, and a hash set of strings on the right as a value. So essentially what I can do with this department list is come up with a bunch of names for departments like computer science, biology, engineering, and associate those department names with a set of students, which I know are string type. Let's go over some usage examples. Once again, my constructor has to be explicitly declared. I call the super constructor to initialize my parents, and then I initialize my own internal fields by calling the new keyword. Then I've got an exclusive university function called formDepartment. I'm going to call departments.put to initialize a hash set as the name of the department. The put method essentially installs a key value pair into our dictionary. This is like adding a word to a dictionary in real life. Here, maybe I'll pass in form the computer science department, and I'd like to start it out with an empty set of students. On line 24, my function enroll is going to take a string student, just like the school's enroll method, but this time I'm going to make it override the school's enroll. I will call the school's enroll method so that I add that student to the list of students, to the set of students, but I'm also going to add that student to the undecided bucket. Remember that undecided was this hash set, and students arrive to this university undecided in terms of major, so I'm going to still do the same thing as what the school implementation does, but here I'm going to do the specialized behavior of adding that student to the undecided set. Line 29 features a new method called joinDepartment, takes two arguments, a string student and a string department, and I'd like to place the student into the department. I'll start out with this guard statement here. If the department set does not contain the department I'm looking for, return. This is as if the student has requested to join a department that doesn't exist. I need to initialize it first by calling the formDepartment method. If I reach line 33, I know the department must exist. I'll remove that student from the undecided set and then add them to the particular department set. Here we can break this down as the departments, which is a dictionary, from department name to set of students. I'll retrieve the set of students associated with that department name, and then I'll add the student target as the first argument into that set of students associated with that department. So this university class essentially behaves like the school class. I can accept students, but it adds some specializations to sort them into undecided or different kinds of majors in different departments. Here is once again a custom override method definition of toString. Here I'd like to actually list out all the students and their respective departments. I'm going to go about doing this once again using string.join, but what I have to do is actually walk all the departments to make sure I get all the departments and all the students. I'm going to do that using the for each loop. We've talked about this briefly in Project Zero and how I can have an iterable on the right-hand side and then retrieve individual elements outside of that iterable by using this for each loop construct that has this colon in the middle. What this is going to do is it's going to create an iterator and then pull out the values from the iterator and assign them to the string department. So what I effectively do here is walk through all the departments. The key set method returns an iterable of all the keys available in the department, so all the names of all the departments, and then I'm going to walk through all those names. Then I'm going to compose the list of students within the department by performing a call to get on the definition for departments, so retrieve the set of students for the particular department. Then let's go ahead and add it to my ongoing list of department students, adding some brackets here so it's nice and well formatted. Finally, I'll go ahead and add the students that are undecided by joining all of them together from the undecided bucket. One kind of fun fact about list constructors, here I'm transforming the undecided bucket, which is a hash set, into an array list. I can do that because array list has a constructor that accepts iterables. This may not actually be entirely necessary because string.join understands how to process an iterable, but I do want to show you this in case you ever want to convert a set into a list type. Finally, I'm going to return the call to get name, so the name of the school, plus the join of all the departments inside the school, as well as all the students within each department. Let's take a look at how that behaves in the test. Here I start out with University NSC, North Seattle College. I enroll the student John, which would place John within the undecided bucket. Then I form a department, Computer Science. Computer Science starts out as empty, and John remains in the undecided bucket. Then I assign John to be part of Computer Science, and that places John within the Computer Science department and leaves the undecided bucket empty. So what we've got here is several layers of extension. We started out with place, which wasn't particularly interesting, it just was a bucket for a name. Then we added the school, which we said was a place, and therefore itself had a name, but also supported a set of students. And then we extended that one more time with university that specialized the school, such that students themselves had undecided or departments associated with. The outcome of inheritance is that child and parent classes form an is-a relationship. A university is a school. A school is a place. However, it's not the other way around necessarily. A place is not necessarily a university. A place is not necessarily a school. We can make a place be a business. We can make a place be a parking lot. It just so happens that these subclasses, these schools and these universities, are going to extend a place and by nature extend the place's existing behavior and properties. We can say an instance of a child is an instance of a parent, but we can't guarantee a parent is an instance of a child. So when I defined that place variable and I assigned it to a school reference, I was allowed to do that because schools extend the behavior of place, and schools automatically fulfill by nature the interface that place fulfills. However, just because I have a place reference doesn't necessarily mean I can assign it to a school reference, because that place could be a parking lot, it doesn't have students, I can't cast it down to a school. Of course, there are some circumstances where it does work. You can imagine I having a place reference that's actually a school underneath, and I'd like to go retrieve the underlying school within. That is an action you can take in Java to cast down the class hierarchy, but it's a bit more specialized, and it definitely requires you go ahead and check in advance whether or not that place is actually a school underneath. The use of a child instance in a place of a parent is called polymorphism. It's possible because the child classes inherently fulfill the same interface as the parent classes. We will talk more about polymorphism next time. Thank you for listening, and I'll talk to you soon.